once we've understood some rudiments of heat transfer, a little bit about heat and stuff, what I want to quickly communicate to you uh, is rudiments of calorimetry. Calorimetry is about heat being transferred from one object to another, or heat being given to an object, the consequence of which could be change in temperature, or heat being taken away from an object, the consequence of which could be temperature reduction. So we'll look at some very simple models related to that. So I know you've in the past in your junior sessions, junior classes, you've looked at some fundamentals of calorimetry. We'll quickly brush past most of them and get comfortable. It would be more of a recap of things that you already knew in calorimetry. Now, first of all, if there is a substance of mass m, if there is a substance of mass m, right, and you supply a certain amount of heat to this substance, call it Q. You supply a certain amount of heat to the substance Q. Then what happens is there is going to be an increase in temperature delta T of this substance. There is going to be an increase in temperature delta T of this substance. Now, what is found is that the heat that has been supplied, and this is change of temperature. I am assuming that the substance is not undergoing change of state. I mean, I'm assuming that the solid is not getting converted into liquid, or the liquid is not getting converted into vapors or gas. So I'm supplying heat which is sensible. Heat is said to be sensible if it results in change of temperature. That's when heat is said to be sensible. So right now I'm looking at sensible heat, heat that you can sense because of a change in temperature produced by that heat. So then there is a certain amount of heat supplied which results in change of temperature delta T. The heat that is given to this substance which results in change of temperature T is mass into a constant S into change in temperature delta T. This S is a property of the substance. This S is a property of the substance and is called the specific heat of the substance. Specific heat of the substance. It's a constant for the substance and is called the specific heat of the substance. And Q is in CGS unit. In CGS unit, Q is measured in calories. So S could be measured in, say, calories per gram per degree centigrade, for example. Delta T, if it is in centigrade, then S, the specific heat of the substance, can be measured in calories per gram per degree centigrade, right? Now, this S, like I said, will depend only on the substance. This S will depend only on the substance and would be a documented property of the substance. You know, experimentally, the specific heat for different substances would be obtained and would be documented and would act as a ready reckoner every time there is an issue related to calorimetry, heat lost by that substance or heat gained by that substance. And whatever I've said of heat gained by the substance, you know, if there is this substance of mass m and it rejects a certain amount of heat Q, that means it liberates a certain amount of heat Q for some reason or the other, then what happens is, then there is a decrease in temperature delta T. Delta T would be decreasing. It will be a decrease in temperature in this case. And once again, the heat that is rejected will again be given by mass into specific heat into decrease of temperature, right? If delta T is an increase in temperature, Q would be the heat assimilated or absorbed. If delta T is the decrease in temperature of a substance, that's because it has rejected a certain amount of heat commensurate with this basic law, right? Ideally, this quantity S, the specific heat of the substance, is temperature independent, but in more sophisticated applications, it is found that the specific heat of the substance actually depends on the temperature regime in which you are operating. If you are operating in one temperature regime versus another temperature regime, you will find a different profile of the specific heat. But for most situations that we are going to look at, and most temperature regimes that we are going to look at, and for most substances that we are going to look at, the specific heat under almost all circumstances would be looked upon as a constant for a given substance. Now, so like I said, the unit of heat is calorie. Now, what is a calorie? How much is a calorie? We must know exactly how much is a calorie. A calorie, 1 calorie, is actually the amount of heat required to raise the temperature of 1 gram of water through 1 degree centigrade is really a calorie, a calorie, right? Now, again, to formally define specific heat of a substance, what is it? It's the amount of heat. As you can see, S in general can be written as Q divided by M delta T, which means what? It's the amount of heat. It's the amount of heat required to raise the temperature of unit mass of a substance through unit degree centigrade. The amount of heat required to raise the temperature of a unit mass of the substance through unit degree centigrade is really the specific heat of that substance, right? That's just a formal way of looking at specific heat. And the unit of Q, mostly calories, and 1 calorie is the amount of heat required to raise the temperature of 1 gram of water through 1 degree centigrade. That's a calorie. That's the measure of 1 calorie. Now, there are times we use a different unit for heat. A calorie, heat, whatever it is, it's actually energy. So there is an equivalent of calorie in energy terms. There is an equivalent of calorie in energy terms, which is joules. Every calorie is a certain amount of joules. And the equivalent of calorie in joules is given by 1 calorie is 4.2 joules. 1 calorie is 4.2 joules. This quantity 4.2 is said to be the mechanical equivalent of heat. This 4.2 is the mechanical equivalent of heat. It translates the unit of heat into the unit of work or energy. So it's called the mechanical equivalent of heat. This 4.2 joules, this is referred to as the mechanical equivalent of heat. Is like 4.2 joules per calorie. 4.2 joules per calorie. Now, so obviously, what is the specific heat of water? Specific heat of water is 1 calorie per gram per degree centigrade. That's by definition. The specific heat of water is going to be, so for water, specific heat S is like 1 calorie per gram per degree centigrade. That's the specific heat of water. That's because of the very definition of calories. Now, having said this, let me also tell you what happens. So, first of all, when you keep supplying heat to a substance, right? When you keep supplying heat to a substance, what really happens is its realization takes place in terms of change of temperature. But after a while, what happens is the temperature becomes constant. If you keep supplying more and more heat to, let's say, a solid, let's say this was a solid, say this was a solid substance, and if you keep supplying more and more heat, initially there is going to be an elevation of temperature. But after a while, what really transpires is that the temperature becomes constant. The temperature becomes constant. And if you keep supplying heat, temperature remains constant for a while. Why so? Why so? Because there is a fundamental change that is taking place in the solid. There is a fundamental change that is taking place in the solid. The solid is undergoing a migration from its solid state to its liquid state. Migration from solid to liquid is taking place. And when migration from solid to liquid that is taking place occurs, then the heat that is supplied at this point does not manifest itself as sensible heat. It does not manifest itself as change of temperature. What it does is every unit of energy that is supplied is actually enabling change of state. A change of state is taking place. A change of state is taking place. In this case, let's say solid to liquid. In this case, solid to liquid, right? And if I have a substance of mass m, then the amount of heat required, and at what temperature would this change of state take place? At the melting point. It will happen at the melting point. At the melting point of the substance. At the melting point of the substance, a change of state from solid to liquid is going to occur. And the moment the substance reaches its melting point, it decides to stay quiet for a while. It does not allow change of temperature. All the energy that is being supplied to it is only fostering and encouraging conversion of m grams or m units of the solid to m units of its liquid. So then we then say that a change of state has occurred, and the amount of heat that would be required to cause the change of state would be proportional to the mass of the substance, the amount of heat that would be required for that change of state. So this time I'm talking of change of state. This heat was sensible heat, but this heat is instrumental in producing change of state. And when this change of state takes place, then the total amount of heat for this complete conversion from m grams of solid to m grams of liquid, from m grams of solid to m grams of liquid at the melting point, m grams of solid at the melting point into m grams of its liquid is actually given by m into L. M into L, where L is a property of the substance. L is a property of the substance. And in this case, when we are enabling change of state from solid to liquid at the melting point, then the value of N that is used, the value of L that is used is called latent heat of fusion. Latent heat of fusion. And what is it? Latent heat of fusion, as you can see, is like a Q by M, the amount of heat required to convert 1 gram of substance from its solid state to its liquid state at the melting point. That's latent heat of fusion. So again, imagine that now I have a liquid, the same liquid, m grams of the same liquid. This is m grams of the same liquid. So I've converted that solid to liquid by supplying how much of heat? Q calories of heat. q calories of heat, right, which has only caused change of state but has not resulted in change of temperature. So at the melting point for a while, there is complete change of state that is taking place, and until the change of state has completely been accomplished, there is going to be no change of temperature. So then I have m grams of the liquid. Same, m grams of the liquid now I have. If it gets converted into m grams of the solid, m grams of solid, then the amount of heat it would have rejected would still be Q. Q would be ml, where L would be, this L would be the same as this L. This L is fusion, whereas this L is solidification. Liquid to solid is solidification. This L is latent heat of solidification. And latent heat of solidification and latent heat of fusion, they have the same value. Latent heat of solidification and latent heat of fusion, they have the same value for a given substance. So if you knew the latent heat of fusion for a substance, then that's also going to be the latent heat of solidification. That means if you knew the value of L, then you would know amount of heat required for m grams of the substance from solid to liquid, or the amount of heat that would be rejected or expelled by m grams of the liquid to solidify into m grams of the solid, right? So that's latent heat of fusion or latent heat of solidification, solid to liquid or liquid to solid. That's a property of the substance. For water, L is 80 calories per gram. 80 calories per gram is the latent heat of solidification for ice. So for ice, the latent heat of fusion is 80 calories per gram, and this is at the melting point of ice. What's the melting point of ice? 0 degrees centigrade. That means if I have 1 gram of ice at 0 degrees centigrade, if I had 1 gram of ice at 0 degrees centigrade, to convert it into 1 gram of water at 0 degrees centigrade, how much of heat would be required? This amount of heat, 80 calories, right? And if I have 10 grams of water, then the amount of heat required would be 10 into 80 means 800 calories of heat. So then, this is latent heat. This is called latent heat, right? Why is it latent? Because it doesn't manifest itself in terms of change of temperature. That's why latent or hidden, right? Heat that will tell you about change of temperature or that produces change of temperature is loud, right? But heat that is only causing conversion of state, let's say in this case from solid to liquid, is latent heat, and it will not show up as change of temperature. It will only show up as change of state, right? So we have latent heat of fusion or latent heat of solidification, which is about the amount of heat required to convert a unit mass of the substance from its solid to liquid state or liquid to solid state at its melting point, right? Similarly, I could have another kind of change of state that is taking place, right? There is another kind of change of state that could occur. You know, I could have had liquid, m grams of a liquid, right? If I keep adding heat to it, initially there would be increase of temperature. Initially there is going to be increase of temperature. But eventually what would happen is its temperature will remain constant. Its temperature will remain constant after a while because all the heat that you're supplying to it is actually causing change of state from liquid to vapor or liquid to gas. So this time the change of state is from liquid to gas or vapor. And the amount of heat, and at what temperature will it take place? At what temperature will this take place? This temperature is the boiling point, of the substance. Is really the boiling point of the substance, right? So at the boiling point, if you supply heat to a liquid, there would be no further increase of temperature. What would happen? It would only cause change of state. By and by, the liquid particles would get converted into vapor particles, right? That is what would happen. All the heat that is supplied would create more spacing, would separate the particles out so that they manifest themselves as vapors, right? And the amount of heat that would be required, so this is like gas, conversion into gas. And all the heat that is required in the process is called latent heat of vaporization. Latent heat. This is latent heat. And the amount of heat Q is given by M into L, where L will be a property of the substance. L is going to be a property of the substance, and it's called latent heat of vaporization. Which is what? The amount of heat required to convert 1 gram or unit mass of a substance from its liquid to gaseous state, at its boiling point, under normal pressure, atmospheric pressure, then that's defined as latent heat of vaporization, right? And one more thing. So now if this gas at the same temperature T chooses to get converted by some means into liquid at the same temperature T, which is the boiling point, then it would expel the same amount of heat. And then L in that case would be called latent heat of condensation. L then would be referred to as latent heat of condensation. And the latent heat of condensation, latent heat of vaporization is the same. And for water at 100 degrees, centigrade, the latent heat of vaporization is, and of course 1 atmospheric pressure, is 540 calories per gram. That means every gram of water at its boiling point, 100 degrees centigrade, at its boiling point will require 540 calories. And when the same water condense, same vapor or steam, right? So, water at 100 degrees centigrade, every gram, if that's given 540 calories, it will get converted into steam. 1 gram of water will get converted into 1 gram of steam if 540 calories is supplied to every gram. Now, if I have steam to be converted into water, what would that process be? That would be condensation. And how much of heat would be expelled in condensation? For every gram of steam that converts into water at 100 degrees centigrade and 1 atmospheric pressure will expel 540 calories of heat, and which is now latent heat of condensation, right? So once we have some of these things in place, it is also important to understand. So this was a quick overview of things that you perhaps already knew from your past. So I chose not to get too elaborate and finicky about explaining things at length, but what is important is now, if there are two masses, M1 and M2, so for example, there could be a mass M1, say there could be a solid, for example, of mass M1 and specific heat S1, and it's at temperature T1, and it's placed in, let's say, a liquid. It's placed in a liquid of mass M2 and specific heat S2 and temperature T2 and temperature T2. And suppose this was a hotter body. This was hot and this was cold. This was hot and this was cold. And I'm assuming there is no change of state. What would happen is heat would flow from a body at higher temperature to a body at lower temperature. Heat would always flow from higher to lower temperature, so there would be flow of heat from this body to this body. And the flow of heat will keep taking place till such time both the bodies have acquired the same temperature T. That means this body of the liquid and this body of the solid, they would have acquired the same temperature T. That's when we say there is thermal equilibrium. Now if I want to calculate T, then what I use is the principle of calorimetry. Heat lost is heat gain. Is heat gained. So realize that the hotter body gets lowered in temperature, and what is the heat lost by the hotter body? Mass into specific heat S1 into decrease of temperature. Decrease of temperature is going to be, its initial temperature is T1, its final equilibrium temperature is T. So it's like a T1 minus T is the heat lost by this. And that must be equal to the heat gained by this liquid body. So heat gained by the liquid body is mass into specific heat, and the temperature of this rises. That means it now acquires the same temperature as this, which is a state of thermal equilibrium. So its gain of temperature is going to be T minus T2. T minus, so this is, sorry, this is T1 minus T, right? T1 minus T, and this is like a T minus T2 is the gain of temperature of this. So heat lost is heat gain. Heat lost is mass specific heat into decrease of temperature for this. Heat gained is mass into specific heat into increase of temperature for this. T is the final common temperature. T is the final common temperature of the two. Right? Sometimes, you know, we also define specific heat is about the substance, right? Is about the substance. It doesn't depend on how many kilograms of the substance. Specific heat is a documented entity obtained out of experiment or other means, and it's only about the substance, right? We have what is also called the thermal capacity. Thermal capacity of a substance will depend on two things: the mass of the substance, M, and the specific heat of the substance, heat S of the substance. Thermal capacity H, the thermal capacity is defined as mass into specific heat. Mass into specific heat. Do you realize if I say mass into specific heat, I could also say it's mass into specific heat into 1, which is as if it's about the amount of heat required to raise the temperature of a given mass of a substance, by 1 degree. The amount of heat required to raise the temperature of a given mass of a substance by 1 degree is called the thermal capacity of the substance, or it's also the amount of heat required to lower the temperature of a given mass of a substance by 1 degree. That's also the heat capacity. That's also the heat capacity or thermal capacity. This is heat capacity or thermal capacity. It's only mass into specific heat. It will depend on how much of the substance. It will also depend on the property S of the substance, right? So once you understand all of this, then you know you are on with the principle of calorimetry, and I think you know we are pretty geared to solve problems. So what I'm going to do is I'm going to look at problems on calorimetry. Essentially heat lost is heat gained, and I think we should be on with it. Thank you so much for this time. Bye-bye.